that our speaker at the February 11th, 2022 general meeting via Zoom will be Dr. Douglas McDonald from the University of Montana. Dr. McDonald studies Paleo-Indian archaeology at Yellowstone. The title of his talk is Before Yellowstone, Native American Archaeology in the First National Park. Our speaker, there will be no meeting in March because of the ESCONI show, which we hope we are able to have. Our speaker on April the 8th via Zoom will be Dr. Walt Kressler of Westchester University in Pennsylvania. He'll be talking about Devonian plants from the famous Red Hill location. The title of his talk, and it's a long title, and he says that we can shorten it if we want to. The title of his talk is Seeing the Forest for the Fossil Trees, Discovering a 365-million-year-old Landscape in Pennsylvania, or Rendezvous at Red Hill, Encounters in the Late Devonian. Yes, we will shorten this title a little bit. A reminder about the ESCONI show on March 19th and 20th at the DuPage County Fairgrounds. Assuming that we are allowed to have it, we will try to have it. Nobody knows what COVID is going to be like at the time. And obviously, if the fairgrounds tells us to cancel it, we will cancel it. But we'll make that decision closer to the show, probably the first week of March. Anybody who's interested in putting a display in the show or demonstrating or volunteering to help, or if you have a donation to give to the club, please let me know. On to our speaker. Our speaker tonight is Dr. Alyssa Abbey. She received a bachelor's degree in geosciences from the University of Arizona and PhD in Earth and Environmental Sciences from the University of Michigan. She had a postdoctoral fellowship at the Berkeley Geochronology Center. Her research interests include tectonics, crustal deformation, surface processes, and thermochronology. Her program tonight is Through the Ages, How We Date Rocks and Geologic Processes.
Thanks, Dave. Good evening, everyone. Should I just do share screen? I'm assuming that's the method here.
Yes, please.
Okay, great. Okay, can everybody see the first slide?
Looks good.
Beautiful. All right, thank you for that introduction. I'm excited to be here with all of you and talking about geochronology. I do focus my research on tectonics and surface processes, their interactions, and using geochronology and thermochronology tools to assess rates and timing of different geologic events. So this is a great topic for me. And I'm also really interested in geoscience education research, so doing that a bit of that as well. And so for today's program, I want to sort of take you on a tour, a sort of broad brush, to look at a bunch of different dating techniques that we use that have been developed over the last few decades. And I'm not going to go into any one of them in great detail. My goal for this evening is to give you a high-level overview of about 10 different techniques and methods we use, but specifically have you thinking about where we use those, what we use them to date, and why they might be important for different geologic processes at different points in time when we're thinking about Earth's history. So as you all know, we have this really wonderful geologic time scale that has been created and calibrated over the years as we get better and better at making measurements. And it covers 4.6 billion years of Earth's history. And so we're going to step through that history and start with the oldest time, which we term the Hadean eon. And so at this time, this is when Earth is coalescing. We see a little bit of water introduction, maybe the moon formation, and we start to see that particles and gases are coming together. There's a lot of heat in the system, but we see some cooling, things start to contract, and we get differentiation, so creation of this sort of layered effect of our planet. And we see that maybe we've got some crust forming at this time. As you've got heavy stuff sinking and lighter stuff going towards the surface, there might be an indication of our first rocks. We've got an idea that there's maybe this is when the mantle started to convect. Maybe this is when we started establishing a magnetic field. And by the end of this time, there's a really important event where we have a bunch of impacts happening where other material that's still amalgamating and hanging out in the region is impacting the Earth. And we call that the late stage heavy bombardment time. So how do we actually know about the timing of these events? Well, the reality is we really don't. This is so long ago, and all of the ages that we're talking about in the 4 billion year time frame have a really large error on them. And it could be 4 billion plus or minus 100 million years. So that's actually pretty decent when we're talking about that far in the past. However, we do have these dating techniques, and the oldest zircons, which are a mineral that are found in rocks on Earth, are dated to be 4.4 billion years old. So that GA that I've put behind the 4.4, that stands for billion years. And I'll talk about billion years, million years, thousands years, and years throughout this presentation, and they'll have different abbreviations. So billion is GA, million MA, thousand KA, and years I will just write as years. But we have rocks, minerals from rocks that we have dated to this old of a time frame. And so there is an indication that we can get a pretty good idea of what was happening in early Earth time. But before we go into details about how we got that age and where those zircons came from, I'll give you a little bit of background on radiometric dating. I'm mostly going to focus on radiometric techniques for this presentation tonight, so having this background will be really helpful as we move forward with all the methods. So if we look at the periodic table of elements, this is showing all the elements that you have on Earth. And when we look at this table, there's also an indication of the mass of each element. And what is important about this and why I'm showing you the periodic table is because you can actually have different masses of the same element. And so we call that an isotope of an element. So when you have an element that has the same number of protons, but a different number of neutrons, it has a different mass. So it's the same element, but it's a different isotope of that element. To give you an example, let's look at hydrogen, for example. So hydrogen isotopes, there are 3 of them. We have hydrogen 1, or protium, hydrogen 2, deuterium, and tritium, 3. So we have 3 different masses for our hydrogen. So representing them with the different balls being the same type of element, but the weights of those balls, so ping pong, golf ball, metal ball, showing the difference between their masses. You can do the same thing with other elements. Another common one is oxygen. We have oxygen 16, 17, and 18, here represented as a beach ball, basketball, and bowling ball. Again, same element, different mass. And so most elements have numerous isotopes. Some of those isotopes are stable, like these ones, and some of them are not stable, meaning that they're radioactive. And radioactive isotopes will decay over time because they are unstable. And what that means is a single isotope that undergoes radioactive decay will then produce a different product, a different isotope. And the different types of radioactive decay don't necessarily matter, but you can have alpha, beta, gamma decay. Those are some of the common ones. And so when each of these processes of decay happens, one isotope changes into another. And we call the initial isotope the parent isotope, and the product isotope is called the daughter. And so I'm going to refer with those names a bunch throughout this presentation, but what we know is that there is a constant rate for this change of different isotopes from their parent component into their daughter component. And so that known rate we refer to as a half-life. And half-life is an equation where it essentially depicts the amount of time it takes for some material that we know the amount of to reduce by half. So if something is decaying, over some amount of time, it will decay such that half of it is left. That is one half-life. And so the equation for that uses this decay constant that we know and solves for that time in half-life. And so you can think about here, just simplified a graph here where time is on the x-axis and the amount of the initial isotope is represented by percentages on the y-axis. So at the beginning of time, you have 100% of a single isotope. As time progresses and it continues to decay, we'll see that that parent isotope is getting less and less than 100%, and we're creating daughter product. And so in this case, if we go from 100% to 50%, that's 1 half-life. So I'll talk about half-lives a lot throughout this, and just wanted to clarify that's the term and what it means. So a lot of different elements have isotopes that are radioactive, and an example of one is uranium. Uranium, the isotope 238, is unstable and undergoes radioactive decay, and it stabilizes once it goes through many different steps of both alpha and beta decay when it hits lead, the isotope 206. And so again, lead has multiple isotopes, just like uranium does, but uranium 238 specifically stabilizes when it reaches lead 208. So this is just a cartoon depicting the decay process of uranium to lead. So if we have half-life information, and we know that that's useful for getting an age, how do we actually get an age from this? So what we can do is measure the amount of this parent isotope and the amount of the daughter. If you have a rock or a mineral, for example, you can measure both of those components. And then we can plug them into an equation to solve for time. That's T in this equation. And so again, we have the measurement from the daughter, the measurement of the parent, and the constant that we know. And from there, we just solve for T in this equation. So that's the age. That's the basics of radiometric dating. That'll be the basis for all the methods that we're talking about today. And so I'm going to take you back to those really old zircons, right? Back to our 4.4 billion-year-old zircons. And as I mentioned before, what's really exciting about how old these are is that this means that this is probably when we had some of our first rocks solidifying and creating a crust. So how do we figure that out? Where those zircons come from? They actually came from a place in Australia. There is a conglomerate, which is a sedimentary rock. So it's actually made up of a bunch of different grains, each one with different ages. And within this sedimentary rock, this conglomerate, there are zircons, one specific type of mineral, that are the 4.4 billion-year-old zircons that we are getting our ages from. The conglomerate itself is also really old. It's like 3 billion years old. So in general, this is a really a place to look at really old events on Earth. But to get the age from the zircons, we used a method called uranium lead dating, or uranium thorium lead dating. And so this is what the zircons look like from the Jack Hills Formation. And all of those circular spots are related to places where the crystals were analyzed with the uranium thorium helium method to get that 4.4 billion-year-old age. So specifics on this method. If we go back to the idea that we just talked about with the parent nuclide decaying slowly over time and creating daughter products, here's a nice cartoon to envision that we've got our zircon crystal that starts with 100% of the uranium 238, for example, and as it decays and produces more of the lead 206, the ratio between that parent and daughter product changes. And so over time, the daughter increases and the parent decreases. And so what's really powerful from using the uranium lead technique is that, in fact, we have multiple decaying isotopes in that system. And so it's the uranium thorium lead technique, although often shortened to be called the uranium lead technique. But because it includes 2 different isotopes of uranium, uranium 238 decays to lead 206 over a half-life of 4.5 billion years. So a very long time to reduce to half of its amount. Uranium 235, which is a different radioactive isotope of uranium, decays to lead 207. And that's a much faster process. And so we're talking about 700 million years, less than 1 billion years for a half-life. And thorium, which is another element in this system that also decays to a stable lead product, the isotope 232 decays at a rate of a half-life of about 14 billion years. So all of these different elements and isotopes of those elements are encompassed in the uranium lead method. And what's even more fun is that the ratio of lead-206 from 238 and lead-207 from uranium-235 is also a function of age. And so we actually have 4 different components that we can use for determining ages. So how do we use all of these different isotopes, and we know their half-lives, to actually get an age? And that's where, for this method, we use what is called a Concordia diagram. And so in this case, on one axis, we're plotting the daughter ratio to the parent. And then on the other one, we're using a different system. So in this case, I'm showing you an example of the 2 uranium isotopes and their 2 lead products plotted against each other. And when we plot them, if everything was perfect, and we know everything with the decay rate is the same, it would make this really nice curved line. And so each of the points on that line are labeled with ages that would correspond to that point. And so this is great. We call this concordant. If we take a sample and we get these different ratios and we plot them on that line, then we can figure out the age exactly of what that rock is producing. And again, you can do this in different minerals within a rock. And so you can have multiple points on this kind of line. Of course, what happens when they don't fall on the line? And that does happen, which we call discordant or discordia. And essentially you can have that happen when, say, for example, a crystal that you're dating has been around for a long time and has been exposed to, say, hydrothermal activity. And parts of it have dissolved and disappeared or have diffused out material. And so you actually lose some of the daughter product. And when that happens, if you're measuring your parent and comparing it to your daughter, you wouldn't have ratios that match to what actually happened in time for that crystal. And so you can then get ages that fall off of this line, this curved line. Another thing that happens commonly with zircon is it can keep growing. So a crystal will start to form and then get bigger and bigger around the edges as different magmatic events happen, for example. And so you can get these rims forming. And oftentimes zircons will show a different age in the center than they will on the outsides. And so that'll be another example when you see points plotting off of the concordant line. That's not necessarily a bad thing. It helps you figure out if stuff has happened to the rock or the crystal. But it is an indication that something has happened. And so again, what's really great about these techniques is that if you using those different systems, they have different precision at different age, at different times. And so if we're looking at really old stuff like we are now in the Hadean, then really focusing on the ratio between the lead-206 and lead-207 is the way we can get really precise ages for geologic events or processes that happened in the billions of years timescales. So what other things happened during that time? We talked about the formation of crust and maybe a differentiation of the core, mantle, and upper crust. And actually there are a few really, really old geologic terrains that exist. It's not just a single crystal in a younger rock, for example, like we saw with the 4.4-year-old zircons. In fact, in Canada, there are 2 places where we have rocks that are dated to be from the Hadean eon. And so, again, we used this uranium lead technique for one of the regions and got a 4 billion-year-old age for the gneiss in Canada. But we also use another method. There are multiple methods, as I mentioned, that we're going to go through, and that can give us information about these older timescales. And so the next method I want to take you through is the Samarium Neodymium method. So again, very, very useful for looking at early Earth or old ages. And similar scenario where we're talking about radioactive decay again. And in this case, samarium 147 isotope decays to neodymium, the 143 isotope. And it has an extremely long half-life of 106 billion years. So again, good indication that this will be great for dating very old events. And so for this method, what we do is actually we compare the daughter product, the neodymium 143, to a stable version of that same element. In this case, that's neodymium 144. And so because we can compare those, then it becomes useful because of neodymium 144 being very stable. And when a rock initially forms, the ratio between the 143 isotope and the 144 isotope is identical. So we know what that is when a rock initially forms. And so if we can plot that, then we would say put it on the parent to daughter ratio, again, is what we're most interested in. And in this case, since we're comparing it to the stable neodymium 144, we put the parent, samarium 147, over the stable isotope neodymium, and then relate that to the daughter neodymium isotope to the stable neodymium isotope. And in this case, if nothing has happened and the rock instantly formed, you would see that different minerals would all plot on the same line, such that the neodymium 143 ratio to 144 is the same. But of course, because samarium is radioactive and decays to 143 neodymium, we'll be adding to that ratio of neodymium to neodymium and taking away from the samarium to neodymium ratio. So in this case, we can look at that, and over time, the ratio of samarium to neodymium 144 will go down, whereas the ratio of neodymium to neodymium will go up. And we can then calculate the age by looking at the slope of that difference from the initial value. So it's a comparison there in this method. This method further advanced in the 1980s when Don DePaulo found out that very old rocks on Earth have ratios that are really similar to what is called the Chur evolution line. You might say, what the heck is the Chur evolution line? Well, the Chur evolution line is the chondritic uniform reservoir. Well, what the heck is that? So essentially, this chondritic uniform reservoir comes from the fact that chondritic meteorites that are of this specific type of meteorite, are thought to be representative of the earliest material that formed in our solar system. And they're unsorted, so it's just all of that material brought together. And so if we have this base of material that is supposed to be early solar system material, and the fact that it's unsorted gives us just this reservoir of material, we call that the chondritic, from chondrite meteorites, uniform reservoir. And so when we found out that the old rocks on Earth are very similar to the chondritic reservoir, we can then use that to compare any other rocks at different times on Earth to that original Chur chondritic reservoir. And so again, we're talking about comparisons here. So if for those of you who are interested in the mathematical component of this, we compare the daughter neodymium to the stable neodymium in this Chur chondritic reservoir to the sample that we're interested in. We just compare those ratios, and that comparison is called an epsilon value, an epsilon notation. So in this case, because we're looking at the samarium neodymium system, it's epsilon neodymium. And so again, because we can compare that to a known value from this reservoir, you can take the deviation of the your sample, compare that to the chondritic reservoir, and obtain an age. So again, the samarium neodymium method is comparing to other known information. So we'll keep moving through time here. After the Hadean, we move into the Archean. We start to see some semblance of continents, not just crust, but actual continents. Maybe there's some tectonic activity, formation of different rocks, some very old rocks. A lot of the very old rocks that we know on Earth are called banded iron formations. We see the introduction of oxygen. Oxygen fluctuates and continues to as we move forward in time into the Proterozoic. And we start to see some maybe life forms, some little amoeba and things. And the biggest thing that I want to point out here is there's this idea that there was a time when we had a snowball Earth, a time when the Earth was pretty much completely covered in ice. And one of the ways that can happen is when all of the continents can come together in one spot. So that would be a supercontinent formation. So how would we be able to date supercontinent formation, for example, and relate that to the relationship of each of the continents and where they are on the globe? Well, we use paleomagnetic data to reconstruct where the continents were at different points in time. But to get information about age, we can use the uranium lead method. So going back to that method we've already talked about, you know the details of so far. But what's interesting is that you can't use this method in zircon, which is most commonly used in when we're talking about paleogeographic reconstructions. Because the rock types that we use for paleomagnetic information don't really have zircon in them. And so instead, we have to use a different mineral. So what I want to point out here is that all of these methods can actually be used in a bunch of different minerals, not just one, not just only in old rocks, but can actually span different timeframes and using different minerals from different rocks. And so in this case, if we wanted to date these paleogeographic reconstructions, we use the uranium lead method in bdelliite. So this is a mineral that you can find in the same rocks that you'd be using for paleomagnetic reconstructions, for example. So if we keep moving forward, we're now in the Paleozoic era, and this is where things get really exciting. We have the explosion of life. You start to see big oceans, lots of deposition of different sedimentary layers. And near the end of this, a proliferation of land plants. And when that happens, there's a lot more of organic material that gets incorporated into the geology. And in fact, near the end of the Paleozoic era, there's a time called the Carboniferous, which is really named that way because of the amount of plant life and trees that were there and ended up in the geologic deposits after being, after living their lives and becoming deposited with the sediments. And so this is where we get a lot of our coal, a lot of our oil and gas reserves are coming from units that have lots of organic material. So can we actually date the organic material? Can we actually date the oil, for example, the formation that it's coming from? And the fact is we really can. And the way we can do that is by using the Rhemium Osmium system. So the Rhenium Osmium system is useful because rhenium and osmium are part of shale, which can be differentiated into two components. The hydrogenous component of shale, which essentially is the component where organic matter extracts rhenium and osmium from the seawater in that component. And the other component is the detrital component. So this is where we see the classic quartz, feldspars, more of your felsic minerals. And so in this dating technique, you can actually separate the hydrogenous component from the detrital component. And that's how we can start dating more of the organic component of the rock rather than some of the other minerals. And so going in detail, the isotopes we're looking at here is rhenium 187. That undergoes beta decay until it reaches the stable osmium 187, which has a half-life of 42 billion years. So again, we're still in the really old time frames here. And the way we determine the ages is really quite similar to the way we use the Samarium Neodymium method. Again, we're doing a comparison here. We've got both values that we know, and we do a comparison between them. In this case, we're not using epsilon notation like I talked about with the Samarium and Neodymium. It's called gamma notation in this case. So here's the equation for those of you who like looking at the equations. This is how we get our gamma notation, again, ratios of our stable and unstable elements and daughter products. And we're relating that to what we've termed the primitive upper mantle. So again, very similar to this chondritic reservoir we talked about for the Samarium and Neodymium. Essentially, this is a value that has been established for what early Earth's mantle was composed of. And so every time we use this method, we compare it to that baseline. Okay, so if we can date oil, can we date other economic deposits? Definitely. So a lot of the mines we use, where we are mining for different ores, for example, have lots of information on ages of deposition, ages of ore formation, and ages of alteration. And so again, you can continue to use the rhenium osmium method, which is great, or you can use rubidium and strontium. So again, very similar to the Samarium Neodymium. We're back to using epsilon values and comparing to a bulk Chur chondritic value. And in this case, we're talking about rubidium 87, which decays to strontium 87, again through beta decay. Also a very long half-life, nearly 50 billion years. What's really exciting about dating ore formations, though, is that not only can we date the minerals that are part of the the ore itself, well, the economic component, but we can also date the alteration of the silicate minerals around it. So when this happens, alter other minerals, some of those more felsic minerals. And when we can date both of those components, we get a lot more information on the sequence of events. How did this ore form? And maybe you find other places where some geologic similarity might happen you could use for exploration of other ores. It gives us a lot more information about the process. Is it this, then this? Is it forward, backward? Is it all of this happening at the same time? And so that's a really interesting thing about dating ores, is that it's not just one mineral. And in this case, you would be able to date a bunch of different minerals from the same deposit, from the same ore formation, to get a lot more information about when and how to find out where there might be other places with similar processes happening, or that similar processes have happened back in time. So again, I'm emphasizing the fact that you can do many different minerals. Other places that we are interested in that minerals grow essentially for every rock, obviously, but igneous rocks in particular, where minerals are growing straight out of magmas. Places where we have large pluton emplacement or dike emplacement, for example, are of interest, looking at magmatic activity. And then of course, super eruptions. We can date big volcanic eruptions and look at the rates at which those happen. And again, by looking at the whole system and not just a single mineral, but maybe looking at surrounding rocks or anything that was already there before the intrusion or before the eruption, we can get a lot more information about the event, not just time, but also process or rate. And so to get at dating some of these other minerals, we can use our classic methods we've already talked about: rubidium, strontium, uranium, lead. But I'll take you into a new method here. We can also use potassium argon or argon-argon methods. So again, we're going into a new method here, which is very useful for dating a lot of these intrusions, especially if they are mafic intrusions or extrusive events like volcanic eruptions. The potassium argon method involves the decay of potassium-40, which can either become calcium-40 or argon-40. But what's really has been exciting in this field is that the method has branched, and there's now a new version of the method, which we call argon-argon dating. And the reason why this is so exciting is because argon-40 is produced from potassium-40 in decay, but argon-39 does not actually occur naturally. And it only has a half-life of 269 years. So why would this be helpful? Well, one thing that came out of this expansion of this method was that we can actually create argon-39, which doesn't exist naturally, by irradiating potassium-39 in a nuclear reactor. So you like force potassium-39 to make argon-39. And because we're doing this and we know exactly what's happening in the nuclear reactor and we know how much potassium we've got, we know that the amount of argon-39 is completely proportional to the amount of potassium-39. And because potassium-39 is related to potassium-40 and they are proportional, then we can actually compare argon-39 to argon-40 to determine the potassium-argon ratio. And so the most exciting thing about the argon-argon method is that you never have to measure the potassium. All you have to do is measure the argon. If you measure both the argon-39 created from the nuclear reactor and the argon-40 that were already in the crystal, don't need to measure the potassium. And you can already get your age by essentially determining the potassium-argon ratio. This is all very exciting, except there's one caveat to the potassium-argon and argon-argon method, and that is that argon is a noble gas and diffuses out of crystals when temperatures get a little hot. So if you have a crystal that hangs out at a fairly warm temperature, we're talking, 500 plus degrees Celsius here, but on Earth, that's not too hot if we start getting deep or we're near magmatic reservoirs or something. And if that crystal is near that heat for a long time, the argon can actually diffuse out of the crystal. So you lose some of your daughter product. So if you get a rock that has undergone this heat perturbation and you don't know, and you measure the argon and the potassium, the ratios are going to be off and your age will be wrong. So that's one thing that's like, oh no, if this happened, maybe this is not a great method. I beg to differ, because what's really cool about this method is you can actually see some of that diffusion in the profile of a crystal. And so in the graph here, what I'm showing you is that you can track the release of argon from the crystal as we're dating it, and plot it on a plot here where the age shows, based on your argon and your potassium ratios, what the age should be. And you can see in this example here, on the left side of the graph, where a small amount of argon has been released, the age is 45, 60, 70, it's growing, it's changing. And then when we get to about 100 million years on this particular graph, it plateaus. And so that plateau tells you that this is the age that we should assign to the crystal, whereas the edges of the crystal, that first age we got of like 45 or 50, is probably not a valid one because of this diffusion problem that happens with argon. And it's not really a problem because, in fact, argon methods could then not only be used as geochronometers, but as thermochronometers. So I won't go into thermochronology now, and I'll touch on it really quickly at the end, but keep that in your mind. Argon methods are actually dual in the sense that they can be used both for geochronology and thermochronology. All right, so let's keep moving through time here. If we step into the Mesozoic era, we're now in the age of the dinosaurs. And what's exciting about rocks and geologic events that have happened from the Mesozoic to present is there's a lot more records of them. They haven't undergone tons of metamorphism, they haven't been destroyed or subducted. And so the records are more proliferous and they are better. They're not just a single grain here and there or a single deposit here and there. We can actually corroborate around the earth, which is great. And so what's exciting about this era is that we start to see a lot more places that we can compare, say, something that happened in Colorado to something that happened in Montana, to something that happened in a different country or a different continent, because there is rock record left. And up until this point, I've mostly been talking about igneous rocks and dating minerals from igneous rocks, but we can also date metamorphic rocks and metamorphic events, as well as sedimentary rocks and sedimentary events. So the thing that's a little bit more nuanced about dating metamorphism and sedimentation is, are you dating the rock or the event? And so in this case, we think about metamorphism, we're recrystallizing previously crystallized minerals. So something that was already a rock gets heated and put under pressure and becomes a new rock. And so we can use some of the same methods we've talked about before: samarium, neodymium, uranium, lead. Another method is called lutetium hafnium, which is the same as samarium, neodymium, or rubidium, strontium, same comparison to Chur, epsilon values, etc. And so we're essentially dating that new rock, which is now a metamorphic rock rather than an igneous or sedimentary rock, whatever it was before. And so we've lost all of the previous information if it's undergone full metamorphism. And so another similar interesting component comes up when we want to date sedimentary rocks. So if you think about a sedimentary rock, it's made up of a bunch of different crystals that have moved all over the Earth's surface and then reformed into a new rock. So same as metamorphism, where there is a lot of information from the previous crystals, but in sedimentary rocks, they don't get remade. It's not a new rock that has a whole new component. The crystals don't get recrystallized. There's just a bunch of crystals with all these different ages. So if you wanted to date a sedimentary rock, you would probably get some old ages in the millions and billions, hundreds of millions, some young ones maybe, depending on when the rock was deposited, from materials that are maybe tens of millions of years, and you wouldn't have a really good handle on the age of that specific rock formation or the deposition of that sedimentary unit. And that's where we can go back to the rubidium strontium method. And what happens when we're creating a sedimentary rock is, during the deposition of all of those different crystals, the rock undergoes a little bit of weathering and diagenesis. And so little clays or fine-grained materials are formed at the same time as the deposition is happening. And so we can actually take this rubidium strontium method and focus specifically on the clay particles rather than the main grains that make up the sedimentary rocks. So we can get dates from the weathering and diagenesis, as well as, if we wanted to, get information about the grains within the rest of the rock. And sometimes we want to. And that comes into play when, I'm not sure if any of you have heard of this, but provenance dating is a method that has gotten to be really popular and usually referred to as detrital geochronology, and often uses the uranium lead method in zircons. But essentially the way this works is, as I was saying, you have a sedimentary rock with a bunch of different crystals from all over. And so you're actually going to have a bunch of different ages. Well, in this example here, say you've got 3 different mountain ranges, the red, the blue, and the yellow, and there's some rivers that are eroding, pulling sediments down and depositing them in a basin. And now you have a sedimentary deposit that might have components of red, blue, and yellow, right? So maybe some old mountains, maybe some medium young mountains, maybe, you know, a combination. And so you can actually use this to your advantage. And getting a population of different ages from one rock sample will tell you where those grains came from. So in fact, you could potentially figure out where paleo rivers were in existence and flowing and pulling material from. So this is a common technique used when looking at sedimentary rocks. And in this example here, they're comparing basin deposits to modern river deposits. And so the way this that we look at the ages from these rocks is in these graphs where age is along the x-axis, and the peaks that are the colored peaks on this image here are showing you how many grains have that specific age. And so looking at this, you can see that there are a bunch of different populations of ages, things as young as 20 million years, all the way up to 80, all the way into the almost 200 million years from this particular study. And so you can use that to say, well, at this time, maybe crystals were coming from the mountains over here, but then perhaps there was a reorganization of rivers, drainage, deposition was coming from somewhere else. And so it's actually a really useful component to dating sedimentary rocks, is getting individual ages from all the grains. So not too sad, we can kind of do a combination of intergrain dating and clays within the sedimentary rock to get a full picture of the sedimentary deposition. All right, so we'll keep moving forward in time. Cenozoic, now we're really getting into some of the younger, more recent activity on Earth. And this era specifically starts with a huge catastrophic event, right? So the beginning of the Cenozoic is marked by the extinction of the dinosaurs caused by an impact, a huge impact. So how did we figure out the exact timing of this impact and the beginning of the Cenozoic era? This time frame is specifically referred to as the Cretaceous Paleogene boundary. So Cretaceous is the last period of the Mesozoic, and Paleogene is the beginning of the Cenozoic. And so this boundary is actually visible in rocks all over the world. And so, of course, it's very interesting to try to figure out if we can date the exact timing of that event. And in fact, we can, and have done some really neat work on this. There was a study in Montana where essentially that location was found where you could see the boundary, really big difference between the rocks that were deposited in the Mesozoic at the end of the Cretaceous to the point where the impact occurred and extinction was underway, to the point where we had full recovery and we're back into the Cenozoic. And so the way we were able to determine this is actually go there and take multiple samples from a stratigraphic sequence. A sequence where there was sedimentary rocks and volcanic tuffs, sedimentary rocks, volcanic tuffs, sedimentary rocks. And within that, you could see also a bunch of different fossils, fauna that were changing. And so we actually used the argon-argon method on all of these interbedded tuffs to find a very precise age for the Cretaceous Paleogene boundary at around 66 million years. But the most exciting thing, I think, is that not only could we get that age, but we also were able to see how long the extinction lasted. How long was the fauna undergoing the disastrous loss that happened? And it actually was 70,000 years after the impact where this extinction of all these different animals and plants was happening. And then on top of that, we were able to find that recovery of all of those plants and animals and just the ecosystem in general took another 900,000 years. And so just with the argon-argon method, we were able to pinpoint the extinctions, the sedimentary accumulation rates between the tuffs at different times, and have really, really good calibration on the geologic timescale. So you may ask, well, what about the meteorite? Can we date that? Well, we could, if we could find that particular impact. We can't, we don't have an actual sample of the impact that created this, this huge catastrophic event, but there are tons of other meteorites that we can find and have dated. So for example, here's one from Meteor Crater in Arizona. We can date meteorites, again, using those very old dating methods. And by old, I mean the method itself is not old, but the ages that we're trying to get are old. So that's the rhenium, osmium, and uranium lead. Again, you've heard of these. We've talked about them a bunch now. But another cool thing is, what if we could not only get the age of the meteorite, but figure out how long it had been on Earth? And we can do that too. So there's a fairly new technique, only a couple decades old here, called cosmogenic radionuclide dating. And that's what we can use to figure out this, how long has the meteor been on Earth kind of thing. And so with this type of dating, what happens is cosmogenic rays that are up in space, they enter the atmosphere and they hit other nuclei in our atmosphere. So for example, oxygen-16. When that happens, that collision happens, they create a nuclide, a cosmogenic nuclide. And so for example, that might be beryllium-10, so a beryllium isotope. This particular collision and creation of a cosmogenic nuclide is called spallation. So when this happens, more collisions are happening, more neutrons are made free and happening and collide into other things. And so you have these reactions happening all over the place. Of course, we can't see them. They also happen down on the surface of the Earth in the soil. So some of those particles make it all the way down and start to create these reactions in the soil. And so you start seeing some of this beryllium-10, or another common one is helium-3, that are created at the surface of the Earth. Interestingly enough, these particles, as they fall down, can really only penetrate the soil about 3 meters. And so cosmogenic radionuclide dating is perfect for thinking about surface processes and thinking about when things are on Earth's surface. So again, that can be used for a bunch of different things, but one classic example is to look at ice flow paths or water flow paths. And so in that kind of a scenario, say you have a big glacier and it's retreating. So as these cosmic rays are coming into the atmosphere, creating spallation reactions, and then hitting the surface of the Earth and creating more of these, the rocks are taking that up. And so they could be taking up beryllium-10, or in this example, I'm using chlorine-36. So again, just an isotope of chlorine. And so in this case, you have a glacier, say that's retreating. When it retreats, it exposes new rocks to these cosmogenic nuclides. And so in this case, how do we get the age? First, we can measure the concentration of the produced isotope, right, after those reactions. We know the rate at which cosmic rays come to the Earth. We know the rate at which that production happens. And so we can calculate how much time has occurred since that rock has been sitting at the surface or exposed to those cosmic rays. And I actually have a student working on that right now in Yosemite. She is working on measuring the beryllium and carbon, which is also a cosmogenic nuclide, on rocks that used to be covered by glaciers. And then over time, those glaciers retreated and changed in both shape and size. And so she's tracking the geometry of the change and the timing and rates of change that happened in a small valley in Yosemite. So it's pretty fun. We can also use cosmogenics for a bunch of other surface processes. I'll quickly take you through some of those. One, for example, is landslides. If you have rock sliding, it's exposing other rock, same thing. Collect age data based on the cosmogenic exposure for that. Rivers or other types of erosion for creating alluvial fans and eroding from canyons, things like that, we can also date with this method. Or what about fault motion? You have a fault that slips and exposes a new surface. Now that surface is exposed, and we can date the slip on that fault. And maybe if you have multiple slip events, you could date the rate of slip on that fault. So these are all very, very near surface processes. There's other methods, including one I'll talk about really quickly here. Luminescence dating is very similar to cosmogenic radionuclide dating. I won't go into too much detail here, but essentially with luminescence dating, you have a crystal lattice that has free electrons and holes, and those holes act as traps. And so when a crystal is exposed to ionization radiation, for example, it will induce trapping of those free electrons. But if it's trapped and the crystal then gets more energy from something else like heat or light, then it can release that trapped electron, and what happens is energy is emitted in the form of a photon. So we can actually see with our eyes the emittance, which is part of where the name comes from with luminescence. There are 3 different types of luminescence dating: optical, thermal, and infrared. So those are the types of energy that can be added to the crystal to create that photon. And so in this case, this is sort of a really nice visual example of how that looks. And for this method, you actually have to go into a dark room and look at the emittance, the spectra that comes off from that. And so that's a combination of the amount of ionization that has happened to the grain, the trapped electrons, as well as the amount of light that the rock was exposed to or heat that the rock was exposed to then emit those photons. So we're talking near surface again, exposed to light, exposed to small temperature changes in heat, luminescence dating, cosmogenics, that's all really near surface, but it's also really short time scales. So the decay of these like beryllium-10 or aluminum or any of these other like cosmogenic type nuclides, or the saturation that can happen with light in luminescence dating limits these methods. And with cosmogenics, we can only go back maybe 5 to 8 million years. And I think luminescence dating only goes back about 2 million years. So not great for looking at really old Earth history, but really great for looking at human evolution. And so these techniques, cosmogenic, nuclides, luminescence, they're super important when we're trying to track some of those changes in human history. And how we do that, same kind of method we did with trying to pinpoint that Cretaceous Paleogene boundary. Samples can be taken in layers of sediment. Those sediments have, say, tools or fossil human bones or things like that. Then we can bracket when those different time periods occurred. So just as a quick overview of what we've been able to do, we've used argon-argon dating for looking at ancestral divergence, when people started to stand and walk, when we started making tools. We've used cosmogenic radionuclide dating for tracking migration, the emergence and extinction of Neanderthals, when we started using agriculture, for example, and most famously, I think in the cosmogenic realm, you've probably heard of carbon-14. So that's mostly the one that's being used in these timescales. Luminescence, similarly useful, as we just talked about. But a final one that's very, very good at doing young dating is the uranium series. And so the uranium series dating is unique because we actually use the decay chain of uranium. So instead of just measuring the parent and the daughter at the beginning and end of the decay chain, we use the individual products in between. And so to remind you of what that kind of a decay chain looks like, there's actually multiple steps of decay that happen to go from uranium to lead, for example. And some of those steps have really short half-lives. We're talking days, minutes, hours, right? And so those timescales help control the fact that we can use this technique to measure really, really young geologic events. To give you an analogy, think about how water flows from one bucket to another. The rate is determined by the amount of water in one bucket and the size of the opening at which the water is flowing out. So in this analogy, your bucket is the nuclide in your decay chain. The number of atoms is the amount of water, and the size of the opening is the half-life. And so in this case, if we assume that the initial water is constant, then the size of your bucket will fill at a rate that's proportional to the loss of water and proportional to the amount of water in the bucket. So maybe that's an easier way to think about it, maybe not, but essentially we're using different steps within the chain. And because those steps are very short-lived, it limits how far back in time we can use this, but it also is very accurate with the young dating. So for example, we can use uranium series to date climate-driven sea level change, for example. And that's fairly gradual, say for the last couple tens of thousands of years. So, a relatively slow process on human timescales and a relatively fast process on geologic timescales. We can look at even faster processes like isostatic response. If you remove ice or even rock material from something, that can change your land surface, and we can track the sea level rise from something like that using U-series. Or what's the most amazing thing to me is that we can actually track sea level change caused by a sudden, almost instantaneous action like an earthquake. And so if you have one plate slipping beneath the other and that crust drops down a little bit, that will change your sea level, cause a little baby tsunami, and you can actually track that sea level change to a point in time using uranium series dating. So we've gone from things that we can date billions of years to things that we can date on days, right? In this across Earth's history, which is really fun. And right before we finish up, I'll just mention, I promised I would talk about this, but I'll bring up the idea that it's not just geochronology that we can use, but also thermochronology. And so thermochronology is essentially the same as geochronology, where we have a radioactive parent nuclide that decays to daughter products. If we can measure those and we know the half-life, we can get an age. But as I mentioned, we were talking about the argon system. Temperature is a key component here because the daughter product can actually escape or leave the crystal if temperatures are increased. And so instead of dating the formation of a rock or an event in geologic time, we're actually dating a cooling age or a thermal perturbation age. So here I'm showing you a list of many different systems that we can use for this kind of stuff, but to give you an idea, the uranium, lead, zircon system that we were talking about is sensitive to temperatures above 800 degrees Celsius. And so it really doesn't track anything besides rock formation because once we're at those types of high temperatures, all the minerals are melted anyway. But you can see that a lot of these systems start looking at, are sensitive to temperatures that are less than 500, 400, all the way down to tens of degrees Celsius. And so they're really useful for looking at near surface processes through time, which is really cool. So just to give you an idea of what those might be, you can track fault motion, for example, exhumation and erosion, like we talked about with some of the other events, but it's not just the timing of those that you can track, but also the rate, how fast things are happening. And what's cool about thermochronology is it's not just an age of a rock, but it can also track heat changes. And so we can apply that to looking at aureoles that form around metamorphic core complexes, for example, or intrusions that are happening in the subsurface that we can't actually see, but that change the temperature above them. Or any hydrothermal activity like hot springs, things like that. So I just wanted to give you a quick look at thermochronology because I did mention it before, and it is a really, really useful technique that's sort of a subfield of geochronology. So to summarize here, we've gone over, 10 plus different techniques. And through this, we've talked about the formation of rocks, different geologic events in time. We've gone through the whole history of the Earth, looking at events that happened 4.5 billion years ago to things that happen in our daily lives now. And the biggest things that I want you to take away from this are that we have new methods that are developing always, constantly. We keep making them better and better. Precision and accuracy is getting really, really good as we increase the accuracy of our instrumentation. The most exciting thing to me, and what hopefully you've been maybe thinking about this entire time, is how can we combine different methods? Maybe they have overlapping time sensitivities. Maybe they could have been used in different parts of the world, but never trying to look at the same kind of thing. How can we combine those to get a better understanding of not only the timing of events, but the processes, how the events happened and how fast they happened, what kinds of rates these things are happening on both Earth and other planets, as we're starting to, see potential for returning rocks from Mars, for example. So with that, I will say thank you. And hopefully you have a much better understanding of a bunch of different techniques we can use for dating now.
That was awesome.
Yeah, wow, thank you.
Amazing. Thank you, Alyssa. I have a quick question. With regard to the old Earth dating processes, what is the actual technology that's used for that? And is it consistent with the various isotopes?
Yeah, good question. I did not go into like the specific, sort of lab components to this, like how you actually get a crystal out of a rock and then measure the information. But most of it is done. We have the instrumentation is getting better. And part of what's fun about this is ages that were determined 6 or 7 decades ago are now being looked at again, and we're able to like pull down the precision on those as well. But some of these techniques essentially involve using lasers to heat portions of crystals. And when you heat that, it essentially makes all of what was in that part of the crystal into a gas that can then flow through a tube, and you can measure all the elements within that. So all the isotopes within that gas get measured and put out through, there's a bunch of different instruments, but usually they're mass spectrometers. That's the like main component that people use. But it's not just lasers. You can heat a whole rock and release gas out of it that way. You can dissolve a lot of the crystals in some very dangerous acids that is maybe not necessarily the most fun lab technique, but doing that, you also then have instead of a gas, but you've got a liquid full of all of the materials that were in there. And so some of those older, one thing that's really great about some of those techniques that we use for early Earth or old dating is that they are also the older techniques where people have been working on them for about 100 years in some of these cases. And so although maybe the original run of dating of some of these rocks produced a much larger error because our instrumentation wasn't good, or we didn't realize that there was contamination happening in different lab scenarios, we've been able to return to those. And so as the instruments get better, we can go back to the same rocks and get more minerals out of them. And so the laser precision is really good. In fact, nowadays you can get laser spots that are down to 15 microns. And so that is, if you think of a micrometer, if you think of 1 meter split by 100 millimeters, split that by another 100, and you've got your micrometers. So we're talking about a laser beam point that is 15 micrometers in size. And so if you have a crystal that is, say, 100 microns, you can actually get points all over that crystal to get a really good representation of the age.
How are some of the really long half-lives determined?
Yeah, I think, well, again, something that people were doing hundreds of years ago is messing around with observing some of these nuclides and in isotopes and how they're changing. And so a lot of the work, obviously, that Marie Curie did was, seeing that there's this radioactivity changes the isotopes and changes the elements themselves. And so part of the determination of that half-life is kind of doing the same thing you're talking about here, where you have a bunch of material that you have a known value or a presumed known value of something and keep measuring it and see how fast it changes. Of course, if you're talking about rocks, then we don't know what the original value was, but a lot of times we can sort of input elements into, say, a piece of metal or a rock that we've like completely gotten rid of everything in. So you've got like sort of a laboratory made rock. So a very pristine made rock with nothing else in it. You can put it into a nuclear reactor and shove a bunch of uranium nuclei into it, for example, and then observe and measure what's happening and then calculate the rate from that. So a lot of that was done in that method. There's also just theoretical, there's a bunch of mathematical calculations that can be done, which obviously I didn't go into in any detail here, but using the relationship between a bunch of these elements and what we know about stars, it's actually almost like a astronomy, astrophysics question at that point, where we know the rates at which different reactions happen in stars and supernova and things like that. And so they use that same information to back calculate some of those half-lives. Sort of a combination, I guess, like some of the really famously studied ones are, and the ones people really care about, like uranium, have been measured in the lab, where other ones, it's sort of like more of a mathematical relationship between similar elements or things like that.
I have a question. It sounds to me like very probably expensive equipment's required to do this dating. Is there basically commercial labs that do this on behalf of all sorts of institutions? And, I'm thinking about, somebody's, all these dinosaur digs and different things that they're doing now. I know they can rely a lot on the geology work already done, but if they want to get a very specific date of a site and they collect material, what happens to that? Does that go off to a lab, or how does that work?
Yeah, so it's different for each of those methods. There are a few that I do on a regular basis myself for my own research, and then a bunch that I know people who do as well. So for each one, it's a little bit different, depending on the researcher and their resources. Some people can do everything in-house. And so there are, like you said, some of those commercial labs where there are a couple of really big labs at universities that specialize in one specific thing. For example, at Arizona, at the University of Arizona, there's a center called the Lasercron Center, and they have just streamlined uranium lead dating like in zircons. It is so fast, and so some people can do the whole process of bringing the rock back from the sample site in the field, crush everything up, separate all the minerals. There's different techniques for that separation, but mostly it's density and chemistry. And then you get to the point where you're actually looking at them under microscopes, picking out specific crystals you want to date. And then if you've got the laser, for example, or the mass spectrometer in your lab, you just walk down and it takes, if they've got it streamlined, it can, and everything is all set up and running, it can take, just a matter of minutes to get a single age on a crystal at that point. Of course, the whole process took, days, but usually they wait until you get like a big bulk amount of material that you want to date, so you can run like 100 different samples instead of just one, because setting that up and getting all the gas and everything is definitely a process. And so some people like me, I don't have my own big instrument, but I have all of the processing lab equipment. And so I can crush the rocks, I can separate the minerals out, and I can pick them under a microscope. And then the last step is me taking it to some of those shared labs or labs where you pay a little bit to get them to analyze your samples. And so in the academic realm, there are a lot of labs that I'd say maybe 3 or 4 for each technique that exists throughout the United States. Of course, there's others in other countries. And so, usually you strike up a partnership, maybe you work on a project together and it becomes like, oh, we don't really need to pay for this. Or they've just got it really set up in the sense that it's almost like a business. And so you say, I have 40 crystals that I want to date, and I have them in a package and I send them to you, and can you do it in a couple months, and so there's actually a whole slew of things that could happen. Doing it yourself, sending it off, you can actually go to those labs too and learn from them and do it yourself, which is sort of an in-between time process, so it doesn't take as long as the sending it off and hoping they'll send it back. It's a great way for students to learn. I like to do that. I like to send my students to the other labs, and they spend like a week and do all their analyses in one go. There are some more commercial style that are not academic organizations that I have seen now, where they'll Some of them will even like start by crushing your rocks. You come back from collecting a bunch of samples and you send them a box of rocks and say like, separate my minerals for me. You can do that. And there's a company in Idaho that's really awesome. They're called GeoSep. And they also have a program for students. So again, I like to send students there to see how to separate their rocks in their lab setup versus mine. And so it's actually like there's a bunch of different things that can happen. And again, depending on how expensive the instrument costs to run and how long the analyses take will be sort of how much you have to pay to get your samples analyzed. Cosmogenic radionuclide dating, I think, is the most expensive one of all the ones I talked about today. Part of that is because there's a lot of chemistry that's, I don't know, dangerous. Not really dangerous is the wrong word. You just have to be very careful and wear lots of stuff and stay super, super clean while doing it. And so the process to separate the minerals is really difficult. And then because it's new and fun and everyone wants to do it, the backup for the line to analyze it is huge, right? So some of them have gotten really good. Some of those streamlined ones, it's, tens of dollars for a single analysis. And so you can get, 50 ages with some of these techniques for under $1,000. Other ones, it's more like 10,000.
I have a question on the cosmogenic, and this is just, maybe how much time must pass before something like cosmogenic dating can be done?
So that's a good question. The rate at which different nuclides both are produced, but also the rate at which we know that cosmic rays are bombarding the Earth is, it's hard to talk about like fast and slow in geology time, obviously, because some things, are relative here. And so it's actually a fairly fast rate geologically, in the sense that if you can get a high enough signal to start making enough measurements of concentrations, then you've had enough. And for cosmogenics, I've seen some stuff that is dated down to like 100,000 years really accurately. And so a lot of people have been trying to push that and go down, like say, for example, if you have faults that are actively slipping and you can see a full fault scarp and the whole surface of the fault. I've seen studies where they will be sampling all the way down the face of the fault scarp to see if they can get a good rate, for example, like how many times it slipped or how often it slipped. And not only do you run into the problem like you just suggested, where maybe it wasn't exposed long enough to get have enough of these reactions to measure stuff, but also the stuff that was exposed earlier is eroding. And so you're actually taking away some of that stuff at the same time. And so you make corrections for that. But because of that known rate of cosmic ray bombardment, you can actually get fairly young and extrapolate. So I've seen that a lot as well, where it's like, well, the accuracy of our measurements is low because there's not much, say, beryllium in the sample. There's really not much. But because there's not much, we can use that to say that it's really young. And so how, and then you sort of like add a larger error to it. But some people are doing cosmogenic dating depending on your element too. I mean, beryllium is actually more useful for the older stuff, but you can go to things like carbon, and that's on like hundreds of years. You can do carbon-14 on hundreds of years. And so it's not only the rate the cosmic rays are coming down, but the rate at which those reactions to create the carbon, the beryllium, the aluminum, the chlorine that you have to consider. And so what's been a cool thing that I've been learning about recently is you can actually measure multiple. If you're not getting a good signal from one, for example, if you're trying to measure beryllium and you don't have a lot of it, you can measure aluminum and see what that is. And then we know the relationship between beryllium and aluminum. You can back calculate the beryllium to get a better age constraint and go to younger timescales. Like I think some of the really fast evolving cosmogenic nuclides, we can get down to hundreds of years.
Okay, because I was just, as you were talking, I was thinking, a lot of times we'll find fossils right on the surface. And I'm curious, how long have they been on the surface? And if that would be something that Cosmogenic would be able to determine, or is that something that's a whole different process?
Yeah, I think it depends on how they got to the surface in that case, right? If, for example, a road was cut and you cut along the side of it, that's actually kind of nice because it's the rock is kind of protected from rays that are coming down. And so you'd actually be able to date when that rock was at the surface, but it's now in the subsurface, versus something that, say, maybe experienced like, oh, I'm at the surface, now I'm buried, oh, I'm at the surface, now I'm buried. Then you get sort of these overlapping contamination of times when it was at the surface and times when it wasn't. And so your values won't actually give you a good age. So if you're finding fossils that are at the surface and they're in sediments that you think are fairly young, like the deposition itself of that sediment was really young, you can definitely use cosmogenics for exposure. But you can also try, if you find sediments, say you dig really far down, like more than 3 meters subsurface, and you find fossils there, you can also kind of figure out when the last time that sample was at the surface, even if it's not now.
Mm-hmm. Thank you. It's fascinating.
So how accurate is it rhenium, osmium?
Yeah, rhenium osmium is actually used really, really widely. And I mean, because it is more useful in some of those organic rich soils or mafic minerals and ores and things like that, it's really powerful because you can't use most of the other techniques in those types of materials. And so the accuracy on that is pretty good. Again, it depends on what age you're looking at. The farther back in time you go, the larger error you have. But if we're looking at, say, 100 to 500 million years, then you probably have an error on that that's roughly, oh, I don't know, maybe 5 to maybe 1,000 years in error. So sometimes if your sample is really good and say you have really pure organic material and you have a lot of it and you're able to make a bunch of measurements, then you could get really close. So you've got like maybe 100 million years with the 5,000 years of error. That's like a really good sample. But if you are looking at something that's like 300 million years and your sample's like a mixture of sediment and organic material, and it's kind of like pretty hard to separate out the best components, you could have something that's like 500 or like maybe 300 million years plus or minus 50 million years, you know, which wouldn't be good. And so in that case, you would just say, well, it's partly the sample because it's not a good one to use this technique on. But you can get really, really great dates, especially a lot of the different exploration companies that are curious about working with academics who care more about the ages and less about the process or like how to extract it. Will work together. And the fun thing is that, like, of course, the academics want the pure material to date, but so do the companies, because that's the best stuff for processing. And so it's kind of this like, oh, who gets it for the analysis. And what's great is that these methods use a really tiny amount of material. And so when I'm saying you might have a bad sample that has a mixture of organic and sand in it, you probably just have to walk a little farther and find a better sample. It's not like that sample is useless to you forever, because the amounts of material that you need for this kind of dating, especially with rhenium and osmium, is pretty small, like a handful, essentially.
So if we're looking at sequential cyclothems, can we measure the difference in time between the cyclothems?
I bet you could. I wonder how much material you have. I mean, it would be super cool to do that. I think you'd have to have a pretty good, it couldn't just be a single sample. You'd have to have like a whole, sort of outcrop where you can take multiple bits from the same layer and things,
Yeah, well, material we've got.
Oh, good. Well, so then the next question is like, what's it made out of? What component is the hydrogenous, what component is incorporating the rhenium and osmium versus, how much of the other material do you have?
Well, what we have is a spoil pile from a shaft mine.
Okay.
And it's a big spoil pile. So it has the roof shale, and it has bits of coal in it, and it has gray shale and black shale and coal.
Mhm.
The problem with this is that at some point, part of this pile self-ignited, probably from pyrite oxidation. So parts of this pile have been disk fired, and parts have not. I don't know to what degree that would interfere with things. Probably not anything good for the organics.
Well, if
but
you could
that-
if you could collect them separately such that you know which ones have been exposed to that essentially bisque firing, as we say, then it's that's even more helpful, because you would obviously avoid those to start with, but then potentially would actually use them for future analyses to compare the difference between them.
So we have this issue of dating certain layers in the Illinois basin and certain coals and trying to establish the relationship between them. And we have one set of assumed dates that's been developed over the years through, biostratigraphy, basically. And that tells us one relationship. And then we have this article about the timing of cyclothems, and we know how many cyclothems we have between the two coals, and it tells us something very different. And we don't have any way to work out this relationship because we don't have any firm numerical dates for any of this.
Oh yeah, well, it sounds like you have tons of material. I think
Yeah.
you should definitely use
Literally.
Yeah, seems great.
Yeah, okay, so who do we call?
That's a good question. I don't necessarily work with that stuff, but I can definitely, I gotta think about that, because I know people who have done a lot of this type of dating. In fact, some of the people I worked with at the Berkeley Geochronology Center have done projects where they didn't do the rhenium and osmium at the Berkeley Geochronology Center, but they were collaborators with the labs that did. And I know there are also national labs that have the abilities to do that. That's a good question.
Well, what about rubidium, strontium on the sedimentary rocks to compare with it?
Oh yeah, and rubidium strontium is a much more common technique. Lots of different labs are doing that. You don't have to have a big setup or anything. Well, it's relative again on whether or not you have to, what a big setup is, but there's a bunch of different labs that do rubidium strontium on like a daily basis. So you could definitely do that.
Okay, thank you.
Yeah.
Hey, Alyssa, thank you again for the fantastic presentation. I have a couple, sort of a two-part question. Early in your talk, you showed some magnificent photos of like old Earth localities in Canada. Have you visited any of these?
Oh, I have not. I have never been to those two parts of Canada. I wonder if I can pull them up again. They are really beautiful.
I'm just imagining what it would feel like to be standing on, 4 billion year old rocks.
I know, right?
And the second question, which I guess is also kind of personal, is do you have any like burning questions yourself? You outlined many more, analyses, et cetera, than I was even aware of that these different techniques can ascertain. What has yet been developed, or what question would you answer if the technology existed?
So the thing that has been not bugging me, but has been, tugging at my interest for so long is that a lot of the rates that we assign to events, for example, are determined with these methods because, say, for example, you have a date from one point of a sedimentary section, a date from another, and a date from another, and between that you have to extrapolate rates of either deposition, or say you have samples along the faults and you have to extrapolate for, rates of fault motion, for example. But when you look at events that are happening just now, like a huge flood or a big fire and then a bunch of landslides, it's not a just sort of continuous slow thing that's happening. It's a bunch of catastrophic events that cause large amounts of deposition, large motion, erosion, things like that, that are probably what we are dating. And so either, and this is where it's confusing, either we're averaging too much over these timescales, we're only dating the catastrophic or big events, or we're not dating the catastrophic and big events. We're missing those because they were so fast and instantaneous. And so maybe, because we get an age from one single rock that we don't know exactly what happened 300 million years ago, we have to make an assumption. And that's part of being a geologist and thinking about geology in general, is, you've got this puzzle, but only like 3 pieces, but it's a 1,000-piece puzzle. And you're like, well, I think it's probably cats or something, right? Like, you just, you have to, this is how geology is, which is sometimes a bit sad, but sometimes really fun. And so, so what I'm really hoping for is that there's some way that we can develop, either by combining these methods, which is why I am so interested in this combination, especially methods that overlap in time scales, but maybe have different precision or something like that, at pinpointing, are we just getting a background? Is this one of those events that things are happening, where things are, really, a huge flood or a huge deposition? And you can, of course, there's like other indicators, right? Oh, big conglomerate or something, and all the cobbles are aligned. Okay, maybe you could say that is from like a big, landslide or mudslide or something like that. But there's so much more other geology out there than like these single visibly identifiable events. And I want to see if we can use geochronology as a way to find those, as a way to say, oh yeah, there are 100-year floods, but what about million-year things as well? Or like there are, big deposits of this, certain sediment, but it all happened at once. And because it happened 3 million years ago and our error on it is 3,000 years, did it happen in one day or did it happen slowly over 3,000 years? And that's why the error is 3,000 years on it, So that's why I'm super excited about trying to combine methods that have different sort of, I don't know what sensitivity is not the right word, but that have different, right now have really different uses. So some of the stuff I've been doing is trying to combine, say, luminescence with cosmogenics with thermo and geochronology stuff that is happening maybe in the last 50 million years. And so you can use the thermo and geo, like argon, and some of the lower temperature thermochronology for some of that 50 million down to 10 million years. And then you start incorporating some of the cosmogenic nuclides, and maybe you actually see some of those events. If the cosmogenics can track something that's happening and you can relate that back to the average that you were looking at from the 50 to 10 million year old time, then perhaps we can do that. And so if we can expand and go farther back in time and not just use these really fun new techniques that are being developed, that would be really good for trying to understand what was happening, say, in the Mesozoic or Paleozoic.
One thing that concerns me is that, for example, I work in that we can, from volcanic eruptions, that we can date. The two big ones are I don't know if you're familiar with these, but the two big ones are the Dike and the mill break.
Yep.
Okay.
I've heard of the mill break.
Yeah, pretty much everybody has. Dike I consider more important, but who am I to say? In section, no problem. The dikey is older, it's lower. The Milbrig is upper, it's younger. You can identify them, no problem. When you do radioactive dating, and they've done different techniques. They've done argon. They've done a bunch of different techniques on biotite crystals, on zircon crystals, blah, blah, blah. The uncertainty of the two overlap enough that they cannot be distinguished using radioactive decay. Now, granted, our resolution is getting better, but there's a good chance that because they're, you know, when we're talking about 450 million years ago or so, because they're so far back that technically we'll never be able to distinguish the two bentonites radioactively. Now,
Yeah.
it could be that we, you know, develop, like you say, new techniques are always being developed. I mean, we know where these bentonites are. They're nice, they're contained, they're between rock. I mean, they're nicely displayed for us. We can get them anytime. I've got a couple here in my room if you want them. There's a good chance that we may not be able to distinguish those mathematically as separate entities. And we know, based on all sorts of physical details and stuff, that the two are extremely different. Not just occurring at, you know, different times, but extremely different. But statistically, mathematically, they may never be able to be distinguished.
Yeah, that's why we always have to rely on other observations, right? It's kind of maybe, I don't know if bad practice is the right word, but you know, if somebody comes in and says that this is the age of this, there with no other context, it's really hard to take that for you know, a good age, and that comes up all the time with geochronology, where it is all about what about the chemistry of the rock, what about all the other relationships, is it in sequence? I mean, you can always go back to the relative dating. I mean, before all of this radiometric and analytical stuff, you know, it was all relative biostratigraphy, that kind of stuff, right? So ideally, you're trying to have as many of those dating components as possible to be able to distinguish between different things like that. But you're right, if you get to that old, you know, 400+ million year old time scale,
Yeah.
you're going to have a large enough error that those are going to overlap. And the fact that you're able to see them and see that they are distinctly different is really what's your best, you know, evidence there that they're different, rather than the age.
And some of the dating techniques they've used, they're down to plus or minus 0.12 million years. So that's 120,000 years. That's pretty darn good.
I know.
And yet they still overlap. So
Yeah.
oh,
Well, and you think about magmatic processes too. I mean, sometimes even just like watching, like just like sitting and watching a volcano, or sitting and watching like those videos that show schematic versions of how intrusions and eruptions happen, there's like a constant sort of flow of new magma that might be a completely different composition that is being added to the system too. And so it would be really cool to be able to like date each one of those. But I think right now it's mostly chemistry based on seeing those differences.
I'm going to stop recording at this point, but please continue with your questions. It's greatly appreciated.
So you
Really
didn't
fascinating.
mention you didn't mention dendrochronology. Is that anything